طيب بسم الله الرحمن الرحيم. So فاحنا اتكلمنا we started to talk about the pseudo-random generators. The pseudo-random generators are the basic ingredient for the stream cipher. So for the stream cipher, we have a plain text which is coming as stream of bits. So we assume that we have stream of bits coming 0, 1, 0, 1, 0, 1, and so on. And then similarly, the pseudo-random generator should also generate stream of bits. Okay? And then all we need to do is just to take this bit and XOR and create the output. So that's simply what the stream cipher does. There are certain properties here which we need to talk about. Very important properties. And I hope you still remember that from the applied cryptography. One important property is the resistance to errors. The resistance to errors. So if we have a stream, so if we have this is the transmitter and this is the receiver, okay, and you have a stream of bits that are coming in, okay, then what you do is that you generate the random sequence, okay, and then you XOR. And then the XORing is to be sent as the cipher text over the communication channel. Okay? Then what happens, remember, the pseudo-random generator, as we said last time, it's not reversible in the sense that from this generated sequence, you need to be able to generate the key, or you need to be able to reverse it and get the key. Of course, this is not a requirement. In fact, it should not be the case, right? It's not that when you see, because remember, this generation of a sequence, okay, if you know the plain text, you can XOR it and get the generated sequence. So from the generated sequence, if you can generate or reverse engineer, get the key, this is very dangerous, طبعا. So this reversibility is not only, it's not a requirement, it should not be the case. You should not be able to reverse and get the key, right? So it's a one-time thing, okay, or it's a one-way thing, right? But if you have the key on the other side, if you have the same key, because this algorithm is deterministic, right? As we said, the random generation algorithm itself is deterministic. So this is the secret, okay? So if you start from the same seed or the same secret, you should be able to generate the same random sequence, right? But you should not be able to reverse and get the seed, right? So this sequence here preserves the property of the fact that the key is the secret part of this whole process, right? So now, one important property here is, as we said, the protection against errors. So the cipher text itself goes through the channel, right? So you have two factors, either attacker who's trying to manipulate this or channel errors, okay? So because of any external factor, there has been some changes to some bits in this sequence, okay? So the idea is, when I extract, so here I can generate the same random sequence, right? And I XOR it with the cipher text to get the plain text, right? So if I get here the plain text, okay, will that plain text, given the errors in the cipher text, be highly correlated with the plain text at the transmitter side? And the answer is, luckily, or the good news is that for stream ciphers, this is exactly the case. Why? because of the fact that we XOR in TIUR, XORing the same position. The bits are aligned, right? So if there is any error, the error is localized, right? فبالتالي when you come here, the errors will be affected in the same parts like here. Okay? Why is this good? This is good in communication because imagine if you are working over an unreliable channel like UDP. Okay? So in that case, you are sending like a picture or a video or something like this. So these types of errors, if they are tolerable, you will be able to recover most of the content, okay? And you will be able to live with that. So if you have, in the graduate course, we have a big, like small project where they do this experimentally using code, MATLAB and Python, right? So they introduce errors over the channel and they try to evaluate and quantify the effect of this error on the other side. And RC4 is very, very good in resisting the channel errors, whether it's caused by an attacker who's trying to affect the integrity or channel errors affected by the network, right? So that's a very important property now. Type. Why is this not the case for block ciphers?
Because it depends on the whole blocks.
Because of the permutation and transposition that we have to do as part of the encryption algorithm. So if there is any small error in one bit, it affects the whole thing. Okay? If one bit is affected, it affects the block. So if you have 3 or 4 bits changed in the file, you have 4, 5, 6 blocks that are affected, especially command that sometimes if you use modes of operation, you have block chaining. So the blocks, the encryption of one block is dependent on the previous one. So in that case, a simple error propagates in the entire content. And that's, for a reliable channel like TCP, that's okay, because TCP will detect the error anyway. And if you have one bit of error, you have to retransmit anyway, right? So you will keep retransmitting until you get a 100% error-free anyway, right? The problem is, for unreliable channels like wireless, like UDP, things like that, you don't do that. You don't do retransmissions. So you have to be able to live with errors, okay? And RC4 is very good in doing this, okay? Not the block ciphers, okay? So that's a very important property. The other one is, as we said, reversibility is not the case for the case of RC4. ماشي؟ طيب. From an information theoretic point of view, although we don't want to do that in depth, but as we said, the Burnham cipher, it works based on the fact that the cipher text equals to the key XORed with the plain text, right? It's very simple, okay? So the idea is that if you know the cipher text, okay, there is a proof that the probability of the fact that that the key takes a certain value, okay, given that you know the cipher text, okay, interestingly بقى, it's proven using information theory that this is in fact the probability of the fact that the key takes a certain value. What does that mean? This means that if you know only the cipher text, okay, it doesn't add to you anything. Okay? You have to guess the key using brute force. Okay? But the probability that the key takes a certain value, given that you know CTI and 1 PTI, is equal to 1. Okay? So why? Because if you know 1 CTI and 1 PTI, only one, Okay, so if you know the plain text that corresponds to one cipher text, only one, what is the key? It's actually CTI XORed with PTI. Only one. Okay? This is the danger of any kind of stream cipher. It's not protective from a security perspective, and we discussed this before, right? Because it's based on Vernam cipher. It's not based on permutations and transpositions. واضحة النقطة دي؟ It's not based on permutations and transpositions. For all the block ciphers that we have discussed, that's definitely not the case. So even if you have a group of CTIs and PTIs, you will still have to spend a very, very long time to guess the key. واضح كده؟ So that's a very important also property for any stream cipher. They are very much resistive to channel errors, okay? But they are not strong in terms of security. Because if you know only one plain text, you can break the whole thing. Despite this, the length of this generated sequence, it's not based on the length of the key. واضحة دي؟ يعني here, if the length of the key, let's say, if the length of the key is n, does that mean that the length of the generated sequence is n, or is 2n, or is 3n? No. It could be as long as we want. Right? And we'll see how we can achieve this. Okay? So the random generation algorithm should be able to give us whatever generated sequence as long as we want. كمان here, we assume that if you have the same key, the generated sequence here and here is the same, right? And that could still be the case, except that the sender and the receiver, they generate that sequence and there is small misalignment. Okay? So imagine that if there is small misalignment. This will have serious effect on the error at the receiver side. So also synchronization is one of the conditions for stream ciphers, بالتحديد. For stream ciphers, it's a big condition. Why? Because just the fact that the generated sequence is the same, it doesn't mean that they are aligned in time. So imagine if these two sequences at the sender and at the receiver, they are the same, but there is one bit of a difference. Okay? So you XOR at the sender side with the plain text, okay, and then you XOR at the receiver side with another bit. They are the same, but they are misaligned. Okay? Misalignment creates a totally different generated stream, which will affect errors significantly. Okay? يعني unfortunately, if I give you the assignment that we give for graduate students, it's very intensive in terms of programming. So one of the things that we ask them to try is this misalignment, okay? Which has nothing to do with security, but synchronization is one of the things that we study a lot in networks, right? And in many protocols, okay? And RC4 is very sensitive to synchronization, very sensitive. In block ciphers, we do not have any issue of synchronization because you always cipher a block by block and decipher block by block. But here it's a sequence of bits. So any misalignment could cause a big discrepancy. ماشي? RC4 is actually commonly used in some standards like what we will discuss later on as part of the network security course, but we will discuss some security services and protocols that still use stream ciphers. But they have to tweak the key, okay, in order to avoid this property. Okay, and we'll see how. Type. So stream cipher design considerations, the encryption sequence should have a large period. And what that means is, based on the key, the generated sequence, the random generated sequence, okay, could have any arbitrary length. Okay? In fact, based on the key, the random generation algorithm should be able to give us as many generated bits as we want. Okay? So the length of يعني here طيب so but here there is a bit of a trade-off. What will happen if we keep generating a very, very long sequence of random bits based on that key? What will happen is that after a very, very, very long time, the probability that you will generate the same pattern, okay, the same pattern that you have generated before increases. ماشي? And this will break one of the conditions we talked about, اللي هي ايه؟ اللي هي سميناها ايه؟ unpredictability. فاكرين؟ We talked about two conditions for a true random generated sequence, right? Randomness, okay, true randomness يعني, which means that the probability of any bit takes any value is the same. Okay? And the other one is unpredictability, that you should not have some parts of the generated sequence that is highly correlated with another part that you have generated before. Here, if you keep generating this sequence for a very, very long time, after some time, no matter what you do, you will start repeating some parts that you have generated before, and that's not good. Okay, that's why it's a trade-off. Okay, so you can generate as long bits as you want, but if you exaggerate and do that for a very, very long time, you will break the unpredictability. واضح الكلام ده ولا أنا بتكلم في ماشي؟ You will start to break the unpredictability condition. ماشي؟ So that's why what happens is that after, let's say مثلا 2 hours, okay, the sender and the receiver, they should agree on another key, okay, which will break that cycle, and then you can start generating random sequence again. And we talked about this lifetime of the key anyway, right? Even for block ciphers, it's always advisable because this again will facilitate the brute force attack, right? So for block ciphers, if we use the key for a very, very long time, you facilitate the brute force attack. Okay? And here it's the same, but you also have the condition of unpredictability, which will be violated. ماشي كده؟ So these are the properties. تمام. So the more random appearing the key stream is, the more randomized the cipher text is, making crypto analysis more difficult. We talked about this. The pseudo random number generator is conditioned on the value of the input key, as we said, right? So here, as long as the key is the same on both sides, you should be able to generate the same random sequence. However, this random sequence is not reversible. We agree on this. ماشي? So the guard against brute force attacks, the key needs to be sufficiently long. Okay? Because again, if the key is long, you can generate many, many random bits, okay, without having this repetition. So the longer the key, the longer the time you can generate a random sequence without having these repetitions. Okay? So that you can keep the condition of unpredictability. There's another property which has not been talked about حتى in the textbook, which is synchronization. Okay? A property that has not been covered here. ماشي؟ طيب. RC4, this is the only and most common technique in the category of stream ciphers. It has been first designed by Ron Ravis for ICA security in the late 80s, and it has a variable key size. So the key size itself could be variable with byte-oriented operations, and as we will see, It's based on bytes, basically the numbers between 0 and 255. So we have 256 ASCII codes يعني. ماشي? And then these numbers, byte based يعني, and they, for the generated sequence, you try to create some permutations, okay, in this stream of bytes that will allow you to generate a random sequence that affects or that achieves all the properties that we talked about. And we'll see how this is done. ماشي? The algorithm is based on the use of random permutations. So you need to do some random permutations based on the key طبعا. We say it's random, but it's actually pseudo-random because it's based on the key. Okay? And it cannot be extremely or truly random. Okay? Because if it's not based on the key, you will not be able to generate the same random sequence at the sender and at the receiver. In that case, it will not work. Because here, remember, we're still talking about encryption and decryption. So reversibility is a big, big condition here. Okay? So just pay attention to the fact when reversibility is a condition and when reversibility is not a condition. Here it is a condition. For random sequence generation, it's not a condition. Okay? واضح الموضوع؟ ماشي؟ طيب despite the fact that, as I said, that RC4 or stream ciphers in general are not very security protective, okay? They are actually being used in SSL in the early versions of transport layer security services and the web or wired equivalent privacy. So we'll study that in the next chapter, يعني. Or actually the one after it, after the public encryption. So we'll study this protocol in details. This is what we use for wireless. Well, this is the early standard for securing wireless communication. Basically, it's based on in our wireless LANs, okay? When we have wireless LANs with password, okay? So we use just password for the wireless LAN, and we use the password to create some kind of security service for wireless. And this is and because of this, because of the use of RC4, the web protocol is very much breakable. So in fact, there is a very common assignment that we sometimes give to students, but I thought it's trivial. Yani. They set up Kali Linux, and in a matter of 1 minute, they break wireless communication. So you can in fact, if any Wi-Fi LAN uses web, okay, in 1 minute, you should be able to extract the password. In 1 minute. Okay? Because of the fact that it uses RC4. Because of the fact that RC4 is based on the Vernon cipher. ماشي كده؟ So how does RC4 works? So first you have this. I suppose you have studied this in applied cryptography. So I'll go a little bit fast, and stop me if there is anything that's not clear. So you have a state matrix which initially is all the alphabets or all the ASCII codes, which starts from 0 all the way to 255. All operations here are modulo 255, or 256, yeah. Okay. So what is 255 plus 1? 0. Okay. 255 plus 1 is 0. Okay. ماشي كده؟ Because it's modulo 256. ماشي؟ واضحة دي؟ طيب. So from 0 all the way to 255, and you have the key. The key is, again, the length of the key is variable, could vary. Okay? So what will happen is that first we will generate a vector, we call it T, okay? And this T initially is solely dependent on the key. So what we do is that we put all the values, all the bits of the key in T. So the length of the key could be the same or less than the size of T. the size of t is equal to the size of s. It has to be equal to the size of s, right? But the key could be less than this, okay? So how can we generate t based on k, based on the key? It's very simple. We just put all the bits, okay? And then after we finish all the bits, we take the first one and then we put it here. We take the second one and then we put it here, okay? So in other words, the t of I equals to k. So t of I اللي هي t of I ثانية t of I okay صح equals to k of I mod 256. Okay, so which means that we keep repeating the bits here as many times as we want, okay? And then we put the value that corresponds to Ti from Ki, okay? So any bit of this could actually replace 1 or 2 bits or 3 bits or 4 bits, regardless. ماشي? So here we put the bits and then we have to circulate it or repeat it more and more and more as many times as we want.
So the same sequence, keep duplicating it?
Yes, keep duplicating. So that's very easy. Then this is the initial state of S and T. So S is fixed and T is based on the key only, okay? Once we do this, the key gets out of the picture, and then we do what we call initial permutation step. This permutation step is a fixed size step, fixed size permutation, which means that we do this permutation 256 times only. ماشي? Why? We'll see, because actually the random generation, it does not have the length of 256. Can be as long as we want, right? But this initial permutation is of, it's for loop from 0 to 255. So this is based on for loop in 0 all the way to 255. Okay? Type. The way that we do this is that we say, so we will take the value of t, okay? And then we will use it to permutate the state vector S. State vector S, remember, initially it's a 0 all the way to 255. So we need to use t to perform some permutation function on S. And by permutation we mean what? We take all we need to do is just to rearrange some bytes. Okay? We rearrange some bytes, that's it. Okay? So this permutation is based on the value of j. So we take I is an index that starts from 0 all the way to 255. And then for each I, we say, okay, so we'll calculate the value of j. And j is the previous j plus si plus ti. Okay? So j equals the previous value, or of course we start from 0. So initially you have I equals 0 and j equals 0, right? I increments every time, but j does not increment every time. It's based on this equation. The value of j is based on the previous value of j plus si plus ti. ماشي? That's it. And then j, in fact, it's an index of, so you have here I, and you calculate j, okay? Then all you need to do is just to swap si and ji. That's it. You swap si and ji. Okay? واضحة دي? Then I goes from 0 all the way to 255. So the length of this loop is fixed. It's 256 times. We perform it 256 times. ماشي? And every time I keeps incrementing. So for each I, we say, okay, so what is the value of j? The value of j is, in fact, the previous value of j plus si plus ti. Okay? So this J becomes then an index of an item that we have to swap with SI. So we keep doing this. Okay? So واحد يقول لي طب افرض الفاليو دي طلعت bigger than 256. هل ممكن؟ Because everything is modulo 256. ماشي؟ So if the value of J becomes 500, it's in fact 500 modulo 256, which means 500 minus 256. واضحة دي, ها? So we keep doing this 256 times. So this is the initial permutation. Is this enough? No, because this is fixed length. But as we said, to generate the random sequence, it's not fixed. We need as long as we want, صح? So that's why there is a stream generation step. So this is the initial permutation step. So in RC4, you do 2 permutation stages. The first one is fixed with the same length, and the second one is of arbitrary length. So this second one here is actually while true. واضحة دي? So this second one is actually while true. يعني you can generate as many as you want. So this step is repeated as many times as you like. There's no limitation. Okay? Because of the fact that we need to generate a random sequence of any length whatsoever. Type. This step is very much similar, but the T goes away. So the first time, K goes away. In the second initial permutation step, the T goes away. And then all we need to do is just to say the J equals J plus SR. Okay? So here, the I, again, increments, but I here recycles. It's while true. I recycles, and for every time you calculate J based on the previous value of J plus SI, okay, and then swap. Okay? And then the generated value here becomes based on the T, which is SI plus SJ. So you have the value of I, which increments. You have the value of J, which is J plus SI. ماشي? After you swap, then you take the two values, you sum them together, and then you get the S of T, which now is the generated byte. Okay? How many times you could do that? Unlimited. Aywa, yes. Unlimited number of times. You can do that forever. So this random generation is while true. You can generate it as many bytes as you want. And supposedly using this way, the generated random sequence achieves the properties that we talked about.
The doctor, is completely possible that some numbers are not swapped, right? Like some indexes are not weeks.
Yes, which means that the value of J equals to the value of R. Right. Okay? يعني انت وانت بتحسب J, in fact this is one of the exercises that I will post. يعني I wanted to calculate the key, okay, so that when you try to do this initial permutation, okay, the value of J comes out always equal to the value of R, which means that you will not do any swapping. Okay? That's a very interesting thing to think about. Okay? This is one of the exercises really that we can do. Okay? So you can calculate the value of the key very, very easily. So now we studied the block ciphers and the stream ciphers and the properties of each one. So hopefully we have some conceptual view now about the properties of each of these. So let's now talk about the public cryptography. Okay, so in public cryptography, as we know, uses two keys, right? In the book, it talks about public cryptography and message authentication. In many textbooks, by the way, they talk about public cryptography as for encryption. Yani. They always talk about symmetric and public encryption both together. In this book, it's functionality oriented. In fact, we usually not use public cryptography for encryption directly. Okay? We use it for message authentication and for key exchange. We'll talk about key exchange later. But we don't commonly use it for direct encryption. ماشي? We rarely use it for direct encryption. طيب. So we will talk about authentication. So message authentication. So encryption protects against encryption itself protects against the passive attack. But we talked about active attack as well. For active attack, we have the attacks that affects the data integrity, right? And we have the attack, which is man-in-the-middle attack. I can send you a message, and you get fooled that this message is coming from an authentic sender, even though it's coming from me, and I'm playing the man in the middle. Okay? For that particular reason, for every single message in the communication, we need to make sure of two things. First, the message is coming from an authentic source, and the message is not altered. Okay? ماشي? So those are the conditions that we need to for every single message. The message is coming from authentic source and it's not altered. Okay, so those are the two conditions. Here, these are to verify that the content of the message have not been altered and that the source is authentic. So these are the two conditions for message authentication. So we have user authentication, user ID and password. That's another story. So that happens only once at the beginning, but that doesn't mean that every single message is authenticated. Message authentication is different from user authentication. ماشي؟ طيب. So there's a different requirement to protect against the active attack, which is attacks that affects man-in-the-middle or the integrity of the data. So therefore, we have this message authentication as a difference. So how can we achieve message authentication? Someone might say that, okay, so at least the part about authenticating the source is implicitly done by the encryption and decryption, right? Because as long as both of us agree on the key, I can make sure that any message is coming from you, right? Because we share the key. That's wrong.
The key could be altered.
Not only that. How can I verify that you have the proper key, okay, without having certain expectation on the content of the message? Yani, when I decrypt the message using the key on my side, then I get the plain text, but I don't have any verification that this is really what you have sent, right? So the plain text could be anything, and I don't have a way to really verify that you have not altered the message or something. So here they have used encryption in a way to confirm that the user is really authentic, but you need to have certain assumption on the content of the message and need to make sure that this message is really the same message that you expected. So I can really use encryption for authentication, for message authentication, only if I know what the content is. Okay? So they said, okay, so let's come up with another technique that can complement the encryption. Okay? So if I can make sure that the message content has not been altered and I know exactly what's in it, okay, then I verify that you are authentic. Because now I can decrypt and I really confirm that this message is true. Then we share the key. So it must be you and nobody else, right? So that's why they came up with اللي هو message digest or digital signatures. Okay? So what I could do is with the message I can send something here that will make sure, verify that this message has not been altered. Okay? So if on the other side, okay, I can make sure that this message has not been altered and this part still verifies the message, okay, then and only then I can use encryption to make sure it's coming from you because we share the key. So that's why they came up with the concept of message authentication codes, which is a combination of encryption and digital signature. ماشي؟ Yeah, this is how they thought about it. Yeah, this is the thought process. Yeah, someone who is really thinking about these are the requirements for message authentication. So how can we do this? Then one thing, okay, so we can do encryption. We know how to do encryption, so we might as well use it for message authentication. But it's not enough. Okay, so if we come up with digital signatures and combine it with this, okay, so now it's enough. واضح? So message, don't confuse this with the physical address. Huh? It's message authentication codes, not MAC address. Huh? Type. So MAC address is actually two things. It's digital signature, which is encrypted. And we'll see this in the next slide. Okay? So message authentication code, it gets added to the message. Okay? It gets added to the message to make sure of these two conditions. هتقول لي طب يعني المسج كده هتتبعت كده. So we can then use encryption again to encrypt the whole thing. Because encryption is for a passive attacks for confidentiality. The two requirements are different. ماشي? So encryption is for confidentiality. But here is for integrity. Okay? And non-repudiation. Non-repudiation here talks about the fact that if the message, if this MAC part is really encrypted with your key, you cannot say I didn't do that, right? Because your fingerprint is in the MAC, okay? So this is what we refer to as non-repudiation. So this MAC affects actually the non-repudiation, and it also affects it mitigates the man-in-the-middle attack, okay? So no one can impersonate you because they don't have the key, right? And at the same time, you cannot say that I did not send that because it's sent by your key, okay? So 3 ways to do this, which we will talk about. But first, as we said, the encryption itself is not enough. So in addition to that, we need digital signatures. So the way that we generate this digital signature is by using the one-way hash function. And see the word one-way. This one-way is very accurate. Okay? This one-way is extremely accurate, and it's extremely important. Because one of the conditions is that it should not be reversible. Okay? So, based on a message of any size, any arbitrary size m, we should be able to generate what we call a message digest or a hash. We call it a hash or a message digest, which is h of m. This h of m is of fixed length, regardless of the length of the original message. Okay? ماشي كده? So, and again, this is not reversible. Okay? So, عشان بس الحاجات ما تدخلش بعضها، يبقى احنا اتكلمنا encryption and decryption, they are reversible. اتكلمنا عن pseudo random generators, which are not reversible, but here based on a small key we can generate a big random sequence. And the purpose is different. Here we talk about hash functions, which talk about a long message based on which we create a hash value. And this hash value is also non-reversible. Okay? And برضو one important factor here is that these hash functions, they do not take a secret key. Unlike the random generators and unlike the encryption and decryption. They are not reversible and they don't take a random key. A secret key. They are not based on secret. All it needs to do, based on a big message, we need to create a small hash value, okay, which acts as a digital signature. Digital signature معناها إيه? If there is any, so this big message of length m, we put a small h of m here, okay? The function of this is that if there is any small alteration or small modification, this hm becomes invalid, okay? So if there is any manipulation to the message, I should be able to detect it right away, whether it's based on hacking, whether it's based on channel errors, network errors, whatever. ماشي? So that's why they thought the simplest hash is actually the CRC codes. Remember we talked about CRC codes in network, right? So they said initially, okay, so let's think about CRC codes. Can they act as hash? Unfortunately, the answer is no. And we'll see why. ماشي? So far so good? طيب, to authenticate a message, the message digest is sent with the message مع بعض. Both. Okay? هتقول لي فين encryption? Encryption is a different story, huh? Encryption is a totally different story. The requirement here is to verify the integrity of the message. It's not for confidentiality here. And that's why we'll talk about security services. In security services, you have to achieve all of this combined. Okay? So we need to do this, we need to do this, we need to do this. So we'll talk about how the protocol looks like to achieve all these requirements all together. But here, the requirement is one-way hash or digest, message digest. Okay. Type. So to authenticate the message digest is sent with the message in such a way that the message digest is authentic. So for that, we can use the key. To make sure that the message is authentic, we can then use the key and encryption to encrypt this part only. Okay? So this achieves the first requirement, which is the integrity of the message itself. If I encrypt this, okay, then I make sure that it's coming from an authentic source because it has the key of that person. Okay? So if I combine two, then I achieve both conditions and everything's good. So that's how they use the hashing, okay? So for message authentication, using one-way hash function. So we do that on two steps. So first, we hash, we create that small message digest, and then we encrypt using symmetric key, for example. Then we create this is the MAC. This MAC now achieves both conditions that we talked about. Okay? So it can ensure message integrity because it has the hash, and it can ensure the authenticity of the source because it has the key. واضح كده؟ I'll finish دي بس بعدين. ماشي كده؟ So this can be done in three different ways. The first one is using symmetric key. The second one is using public cryptography. For public cryptography, we have two keys, right? So which one do we use at the source side? And which one do we use at the destination side? Pay attention here, ba. In normal encryption system, if we use the two keys, and as we know from applied cryptography, we have private key and public key, right? So if I need to send you a message that you need to reverse, okay? Then what happens is that I need to encrypt this message using your public key so that you can use your private key to decrypt it. ماشي? If I need to authenticate you, okay, then what happens in that case is that the receiver needs to authenticate the sender. ماشي? So what does the receiver have about the sender? Does it have the private key of the sender? No. It has its public. ماشي? So that's why for Mac, it's actually the other way around. The sender encrypts the digital signature using its own private key, so that if you want to authenticate me, you can use my public key to authenticate me. Okay? I see from your faces that this was news to you. It's like you did not hear that before. Okay? So that's what happens for encryption and MAC. So public cryptography talks about two keys, private key and public key. Okay? So for encryption, I usually use your public key, okay, so that you can use private key to decode it or to decrypt it. But if you want to authenticate me, then I need to encrypt the digital signature using my private key, because what you know about me is the public key, right? So I need to encrypt my digital signature using my private key. واضح كده؟ مش كده؟ طيب, so for public key that's the case. طيب, what is the problem always of cryptographic algorithms or encryption algorithms? They are complex, صح? So can I do this without using encryption خالص? Yes. We can use بقى ايه? A secret value. This secret value is some kind of a small كده encoded bits based on your user ID, and it's like you take user ID and password and some other parameters about you, and I hash it all together. And مثلا you want to authenticate yourself to a server, so initially you write your user ID and password. This is user authentication. So the server can hash your user ID and password and everything, right, in a secret value that you both agree on. Okay? And then we exclude by encryption altogether. We use this secret value, we add it to the message, and then we hash everything. So this is your key. It's like your key, but it's not actually a key because we're not using encryption here. تمام? So we're using a secret value that we agree on. And usually this secret value is based on your user ID and password, but طبعا not password, not plain text. We hash everything. ماشي? So this way we get rid of encryption altogether, because encryption is complex. It's complex. So I can do message authentication without using, because here again the requirement, there is no need for reversibility of that secret value. I don't need to reverse it. I need to verify it. I need to generate it at my side and verify that it's correct. ماشي? So these are the three methods for doing message. We'll continue inshallah next time. These requirements are very, very important. We'll discuss these requirements in details. I hope you still remember something.